Welcome to another explainer. Today we're going to dive into a topic that literally surrounds us every single day, yet is almost universally misunderstood. We're looking at the surprisingly complex, highly engineered chemical marvel that is modern concrete. This isn't just some gray paste drawing on a sidewalk. It's a continuously evolving, high-performance material that quite literally holds up the modern world.
So let's start with a provocative question just to shift our perspective a bit. How did a basic, age-old mixture of sand, water, and cement transform enough to let us construct super tall skyscrapers and dig massive pressure-resistant tunnels under the ocean? Well, the answer lies in the incredible leaps we've made in material science and microscopic chemistry.
Here's our roadmap to figure this all out. First, the concrete recipe evolution. Second, high performance and high strength. Third, the self-compacting concrete revolution. Fourth, special concretes and composites. And finally, quality control and safety. To really grasp the scale of this, take a look at two monumental feats of modern engineering. You've got the Petronas Twin Towers soaring 451 meters into the sky, and the Channel Tunnel Rail Link, with these massive 8.15-meter diameter tunnels built using 60 megapascal concrete reinforced with steel fibers instead of conventional rebar. Megastructures exactly like these, they're only possible because of radical advancements in concrete technology.
All right, moving into Section 1, the concrete recipe evolution.
I want you to think of concrete mix design kind of like baking. The traditional recipe was super simple: cement, water, sand, and coarse aggregate like crushed rocks. But the modern concrete kitchen has introduced some seriously powerful chemical admixtures. We now use these new generation superplasticizers with an absolute mouthful of a name: multi-carboxylate ether, or just MCE for short. And these are a game changer because they allow for extreme flowability while drastically reducing the amount of water needed, which is key because excess water basically weakens concrete. We also toss in retarders to slow down the chemical hydration process, which gives construction crews more time to actually pour the stuff. But perhaps the absolute most vital modern ingredient is silica fume.
Industry experts Pierre-Claude Atzin and Adam Neville are actually super blunt about this. They point out to reaching incredible new structural limits, pushing reliably past that 60 to 90 megapascal range, was entirely dependent on this one specific microscopic additive. Silica fume particles are exceptionally fine. They literally fill the microscopic voids between cement particles, creating this incredibly dense, impenetrable matrix.
Okay, let's jump to Section 2, high performance and high strength.
So, we measure concrete strength in megapascals, or MPa. And the crucial point here is the staggering leap in these numbers. We've gone from standard 30 MPa mixes, the kind you might see in a typical low-rise building, to high-performance concretes at 120 MPa used in super tall towers. And then, right at the bleeding edge of the chart, we have reactive powder concrete achieving an astonishing 800 MPa. Just to put that into perspective for a second, that is concrete performing with the strength of some actual structural steels. It's wild.
Now, to achieve that unbelievable 800 megapascal strength, engineers had to completely rethink the recipe. Notice what's missing from the reactive powder concrete mix. There's absolutely no coarse aggregate, no rocks whatsoever. It completely replaces them with extremely fine-ground quartz measuring just 4 microns, fine sand, massive amounts of that silica fume we talked about, and microscopic steel fibers. By eliminating the larger rocks, they essentially removed the weak points where microcracks usually form, creating a hyperdense, highly ductile composite.
Which brings us to Section 3, the self-compacting concrete revolution.
Have you ever wondered how thick, heavy concrete could possibly be poured into a dense, complex forest of steel rebar like this one? In modern, earthquake-resistant structures or nuclear power plants, the reinforcing steel is so tightly packed that traditional concrete simply gets stuck. And if the concrete doesn't fill every single tiny gap, you get dangerous voids, which completely compromises the entire structure's safety. The answer to that absolutely terrifying engineering problem was self-compacting concrete, or SCC, a really revolutionary development that originally came out of Japan. You see, traditional concrete requires heavy manual labor and incredibly loud mechanical vibrators just to shake the concrete down into the rebar. SCC, however, acts completely differently. It flows almost like a thick liquid under its own weight. It's completely silent, self-leveling, and easily navigates through those impossibly tight steel spaces without the heavy rocks separating from the cement paste. But creating this magic liquid requires a highly delicate, perfectly structured procedure. You have to perfectly design the paste composition, finding the absolute optimum water-to-powder ratio and superplasticizer dosage. If the paste is even a little too thin, all the heavy rocks will just sink straight to the bottom. If it's too thick, it just won't flow. So engineers verify this balance through really rigorous lab tests, like the V-final and slump flow tests, way before a single drop is actually poured on site.
All right, let's look at Section 4, Special Concretes and Composites.
Concrete is pretty much the ultimate chameleon material. For nuclear radiation shielding, we create high-density concrete using heavy iron aggregates, which brings the weight up to a massive 5,280 kilograms per cubic meter. For ultra-high strength, we impregnate the tiny pores of the concrete with monomers to create polymer concrete. We even use three-dimensional basalt fibers to vastly increase the material's ductility, meaning it's actually going to bend and flex under pressure rather than suddenly snapping.
Just take a look at ferrocement. This technique involves impregnating tightly spaced wire mesh with a rich cement mortar. Notice how it allows concrete to be molded into incredibly thin, flexible, and lightweight shapes. It is so versatile and impermeable that it's genuinely used to build water tanks and, believe it or not, floating boats.
Finally, let's wrap up with Section 5, Quality Control and Safety.
Quality control is conformity to the specifications, no more, no less. Look, you can design an 800 MPa supermaterial in a pristine laboratory all day long, but out in the field, safety relies entirely on the personnel, the mixing conditions, and ensuring the final poured product exactly matches that meticulously designed lab recipe. If a single worker adds just a little extra water on site to make the pouring easier, the strength plummets and suddenly the whole structure is at risk.
Human factors have a truly terrifying mathematical impact on safety. When a site has excellent control, meaning they're using precise weigh batching and continual supervision, the variation in the concrete's strength, the standard deviation, is super tight, just 2.8 MPa. But look at the bottom row. If the site is uncontrolled, just eyeballing volumes of aggregate with little supervision, that deviation jumps all the way to 8.5 MPa. That level of uncertainty is honestly terrifying when you're building something like a massive bridge.
So to prevent catastrophic failure, engineers rely on strict statistical quality control methods found in standardized codes, like India's IS 456. Utilizing the limit state method for design stability, they essentially build a mathematical safety net right into the project. The code mandates that the target mean strength designed in the lab must be equal to the required characteristic strength plus 1.65 times the expected standard deviation of the site. Basically, this formula forces engineers to mathematically over-design the concrete to safely absorb the inevitable variables and hiccups of real-world construction.
The next time you walk past a construction site, or drive over a massive suspension bridge, or enter a towering skyscraper, you won't just see gray rocks and paste anymore. You now understand the highly engineered science, the microscopic chemistry, and the rigorous mathematical safety codes that make it all possible. As we continue to innovate and push the absolute limits of material science, I want to leave you with this thought. What impossible megastructures will the concrete of tomorrow allow us to build next?